All right. Welcome, everyone. Thanks for tuning in. Thanks for being here. Grades are up to date, so if you go check JMC online, you'll see that everything is in the gradebook right now. Everything. I'm talking everything. The only thing that possibly isn't is the constructions we did on Friday, because I'm not back to grab those papers yet. So hopefully I'll be back on Wednesday or Thursday this week. That's the plan. But yeah, we're gonna take a few notes today. So it's gonna be kind of a heavy note day. Sorry, we have a lot of properties to write down. As you can tell from my list here, we're kind of finishing up the postulates and theorems in this fourth unit for us. I know it's chapter 3 of your textbook, but it's our fourth unit test. So we have quite a few notes to take today. So I'm gonna want you to have your notes out, be ready to go, and then pretty much after we're done with notes, that'll be pretty much it for today. Tomorrow might be the day where we get an assignment based on these notes. So it might be a Google form again, just so you can have it. It's a lot of vocab on this one. So now, again, don't focus so heavy on what postulate number we're on. Just kind of know what it says. That's really what I want you to get from this. That's kind of the hardest part about geometry is, I know there's a lot of vocab and a lot of property names, but it's to know what they say, so that you have it in the back of your mind. These are the properties that actually work in Euclidean geometry. So, yeah, I'll let you write these down here real quick if you need to, and then we'll kind of go on. As you guys are getting your notes out, ready to go, we're going to review two postulates we've had. These are the ones we talked about on Friday last week. They're 3, 4, I think was the new one. That was the perpendicular postulate, and then 3, 3 was the previous one. It was the parallel postulate. So those are ones we should have had previously. So, and then the two postulates that were before that were about corresponding angles. So 3-1 was corresponding angles, and 3-2 was the converse of it. So those are the only postulates had up till this point. Everything else has been theorems about alternate interior, same side interior, or consecutive, whatever the book calls them, and alternate exterior. So those are the only ones we've had. I think we've had a weird one about perpendicular. That was like theorem 3, 4 or something like that. Alright. Miss Scott, just let me know when they're good to go and we'll get started here today.
Does anybody need more time to write this bit down? They're good. Okay,
let's jump right in. It's going to be kind of a heavy note day, as I said. Alright, so this is one we had last Friday, so this shouldn't be too new to you. It's the parallel postulate. So it says, given a line and a point not on it, there exists only one line that can be parallel to the given line passing through that point. So let me just draw this out for you again. So we have, ooh, that's a terrible line. So here's my line. I have a point that is clearly not on it. Point that is not on it, I'll call it point P. What this postulate says is there is one and only one line that is parallel to the given one passing through point P. There can only be one. Again, it's a postulate. There you go. Okay, that was one we previously had, so everyone should have this one already. This one we had, I think it was like last Tuesday, but we even reviewed it on Friday last week. So again, how we discussed this one was that we talked about how to draw parallel lines. The construction we did on Friday, if you were not here, we basically drew a line that went through point P like that. We copied this angle up to here, and then that allowed us to draw this line that was perfectly parallel because it made corresponding angles. That's what we did on Friday.
Does anybody need more time to write this one down? They're ready for the next one.
Okay, perfect. Okay, so now 3, 4. This is again one that we had on Friday. This is the newest one. This is the one that it was new to us when we had it. Postulate 3, 4, perpendicular postulate. Right. Given a line and a point not on it, there exists exactly one line that is perpendicular now to the given line, passing through the point. So again, I'll draw the same exact drawing I had earlier. Here's my line. Here's a point not on it. Call it point P. And this one talked about that there's exactly one line that is perfectly perpendicular to the given line. And again, perpendicular meant 90 degrees. That's the little perpendicular symbol, that little box. Now, the symbol in the textbook, just so you know, this is something that I don't know if we've discussed yet. You know, parallel, when we talk about lines being parallel, right? Line L is parallel to line, let's say line, M, right? That's parallel, right? In fact, let me write that. That's the symbol for parallel. But for perpendicular, the symbol we use is we use a little upside down T. That's the little symbol we use for perpendicular. So line L is perpendicular to line M. Upside down T symbol. So if you see that in your book, I want you to be familiar with that. If you tend to look in your book every now and then. So in this particular case, maybe this is line M and this is line L. They're perfectly perpendicular, so this would be the one. So that would be probably the only new bits. Good?
You're good.
Okay, all right, let's move on. Let's get to our new stuff today. So we have a bunch of postulates we have to talk about, but before we do that, we have one theorem I want to cover. I know I'm going a little out of order from that first screen that I showed you. I want to talk about theorem, I think it's 3.8, I think, maybe? 3.9, theorem 3.9. All right, theorem 3.9. This one, it goes with the constructions we did. That's why I'm pulling it up now. Now, to explain how this one works, we have to use a property from Algebra 1, but I'll let you write it down first, then we'll discuss it. So again, theorem 3.9, two lines equidistant from a third. Again, the word equidistant means equal distance. They just crammed two words together, made a whole new word out of it. But it talks about in a plane, two lines that are equidistant from a third, each of them are equidistant from a third, then the two lines are parallel to each other. I'll have to write this one down.
Does anyone need more time with it? Looks like they're ready.
Okay, so let's talk about how this one works. Again, it's a theorem, so we do have to show kind of how it works. Because we can't just take it for granted, we have to show evidence. This one's going to go back to Algebra 1, which I know has been quite a while for some of us. So I want to discuss something. Maybe this is something you guys never got to discuss in Algebra 1. I'm hoping that you did, or maybe that you remember that we did. All right, so let's discuss kind of what this one is saying. So we have a given line. So here's my line, right? And we have two lines that are equidistant from it, right? So two lines that are perfectly the same distance. Okay, whatever that distance is, let's call this D and D for distance. And they're both the same distance from that line. Okay, and we'll put this line over here, and I'll put a different color line on the other side, like that. Okay, the goal here is to prove, I want to prove, and I'll call this line L and M. I want to prove that line L is parallel to line M. And all we know right now is that the distances are the same from the middle line, wherever that line is. All right, so here's kind of the idea what the book talks about. All right, so it talks about that when you have lines that are equidistant from each other, right, that this distance is uniform throughout the entire problem. That means it's non-intersecting, right? That they're equal distance. It's a certain distance apart, and it travels along the whole path. That means that if it's the same distance the entire time, the lines, in theory, have the same slope. So that's something that, from Algebra 1 class that they discussed, that lines that are the same distance apart the entire time have the same slope. They're going the same direction. Slope is that rise or run. We talked about that in the last unit test. We did a lot of Algebra 1 in the last unit, drawing and graphing and doing systems and whatnot. Well, they have the same slope. Well, lines that have the exact same slope tend to be parallel to each other. It's actually a property of Algebra 1. The definition of parallel means lines that do not intersect, they're in the same plane. Well, in Algebra 1, they talk about that they have the same slope. That was a property from Algebra 1 class. Well, these lines that are equidistant, right, this distance is the uniform throughout the entire line, means that the two lines have the same slope. So whatever, let's call this line in the middle, let's call this line T, right? So line L has the same slope as line T. So line L has the same slope as line T. And so that would mean that line L, according to Algebra 1, is parallel to line T. All right, because of that uniform distance between the two. And then same thing on the other side, that the distance here, let me give a new color. The distance up here on these two, this distance is uniform across the entire way. So that means, these two lines over here would have the same slope. So line M has the same slope as line T. So that means line M is parallel to line T because of that same reasoning, right? It's equally spaced, so the slopes have to be the same. In according to Algebra 1, having equal spacing means the slopes are the same, and that forces them to be parallel. And so now this comes to the transitive property, that if I have, and so this is the tricky part that you have to kind of associate here. This is the tough part, that if I know that line L is parallel to line T and line M is also parallel to line T, I don't know, I just wrote tine, but line to line T, then i.e. ... that's a little triangle of dots, line L is parallel to line M. Again, this is a transitive. You can see the connection of dots. When we talked about the transitive property back when we did, the Algebra 1 unit, we talked about, I think the example I used in class was like, two students have the same age, one student is 16, what's the other student's age? Well, you could transfer that 16 years of age to the other kid because I told you they're the same age, you connected the dots. And that's what's happening here. You're seeing that they're parallel to the same line, so they have to be parallel to each other because of that same connection. It's called a transitive property. But it also forces that the slopes would be the same because the slopes are equal to line T, and then that forces them to be parallel. So that's another reason, other than using transitive. Maybe transitive didn't work for you.
Is everyone good with this one? You got it down.
Okay. So, all right. Now, yeah, I kind of warned you. lots of postulates here. I'm just gonna let you write these down. I thought this is better than doing like 50 slides. Hopefully you guys can read these here. So we have postulate 3.5 all the way up to 3.11. A bunch of postulates. Again, we don't prove these. They're just systematically, properties in math that deal with lines and points and all that good stuff. So it was something that I thought we probably should cover. These were scattered throughout your textbook in different locations, and so I kind of combined them all into one page here. Your book has these scattered throughout your textbook. No joke. All right. Lots of postulates. And these all have to deal with lines and points, which is pretty much what we've been dealing with this entire unit, right? We've been dealing with parallel lines and all that good stuff. So how these work and how I always remember them. It's basically like every other one. So maybe if you look up here, all the odd ones deal with lines, and all the even ones deal with planes, pretty much. I mean, that's the idea. Maybe 10, 11, they get a little bit off here, but that's how it works in the beginning. So it always talks about, so the 3.5 talks about a line, 3.6 talks about a plane, then it goes a line again, then it goes a plane again, and then the last one it goes a line, then a plane. So that's how I kind of memorize these. They're always kind of paired together. So it talks about basically how these postulates came about. These are like definitions of the words we've been talking about. So it's kind of a nice little review. Through any 2 points, there's exactly one line. So if you have 2 points, you can always draw one line that connects straight to them. That's how our constructions work. That's why I thought it would be kind of a smart idea to bring this up. That if you put any 2 points on your paper, so I'll just put 2 points down here, point A and B, you could draw one line that goes through them. That makes sense. You could take a straight edge, draw the line that connects to them. And there's only one. Again, they're collinear. But exactly one line connects them. Now, how do we write a line? What's the notation again? How do you write lines again? Anyone happen to know what's the notation to write a line? Going back to day one.
Anybody remember?
Keep going.
You said AB with a line over top.
Yeah. AB, the two arrows on top of it. Nice. Yeah. So, very nice. So, yeah. So, the idea is that you could draw that out, put the two lines above. There's another notation you write, but that's only if you have a cursive letter. I don't have a cursive letter here. The italicized like line M or L. I don't have that here, so I have to use the two-letter system and arrows. If there's more dots on here, that's what we'll see. I think on the which one has 3? Oh, that's a plane. But if there's more than 2 dots on this line, you only use 2 letters. So just use 2. Only 2. That's definition. Very nice. Good call on that one. Alright, so the next one. Through any 3 points, there's exactly one plane. Now, there's a stipulation here. These points through any 3, and what we should put in here, and this is something that the book did not do. I typed it exactly how the book had. These should be non-collinear points. Non-collinear. So maybe you want to make that little notation to yourself. Again, I typed it exactly how the book had it. These are non-collinear, 3 points that are not in a straight line. 2 are always in a straight line, but the third one would not be. So it's called a C, D, and E. So 3 points not in a straight line, non-collinear. There's exactly one plane. So on this particular example, the marker board would be the only plane that could hit all 3 at the same time. if they're in a straight line, you could have a plane that could tilt. What's a good way to put it? Okay. Think of it like, this is a terrible example, but think of it like the Lady of the Lake. If you're familiar with the boat on the lake shore, there, in the back of the boat, it's a paddle boat, right? It's an old-fashioned steam paddle boat. Well, there's a bar on the back of the boat, and then there's paddles that are all attached to it, right? That kind of go in a circle, and it kind of spins around. It's on a big wheel. It's a terrible drawing of it, but you get the idea, and it kind of spins around. Well, those paddles go from the inside out. So if you were to like look at the paddle from the side, they would look like this, right? The paddles would kind of go through, and then there's this, metal ring that holds on to them, so that when it paddles, you can actually see it. And that's the idea that if they're in a straight line, the three dots were in a straight line, that you could have an infinite number of paddles that could touch them. But by putting them in not in a straight line, like my C, D, and E in here, is that there's only one plane that could touch all three at any given moment. Only one. It'd be the marker board. I know it's kind of hard to describe, but yeah. All right.
Does anyone need more time to write this one down? They're good with that one.
Okay. Now, the next one. So now, as I said, like every other talks about a line and a plane. So now we're back to a line again, right? So it's talked about a plane, now we're back to a line. If you have a line that's already provided to you. So I already gave you a line. There is at minimum, right, a minimum of 2 points that you can put on it. So you're always allowed from this point on, if you're given a line, you can add more points to it. A minimum of 2. C, F, G, right? So if you want to put more, you can do that. At least 2 points can go on that line. So from this point on, if you're given lines, you can actually add your own points on it, in case you need the two-letter system to name it. So if I was going to name this line, just like you guys said earlier, you'd call it FG with the little arrows above it, right? The one thing I forgot to write earlier, how do we name a plane? I've talked about lines here, but how do you name planes?
A cursive letter.
Cursive letter? Okay, you could do that. What else? Now this particular example, I don't have a cursive letter on this one. So how do I name my plane here? The one that touches these.
Anyone know of another way? Good.
Would you choose at least 3 points?
Did you hear that?
No, I didn't.
You said choose at least 3 points.
Okay, yeah. Choose 3 points, and what do we have to put in front of those 3 points? What do we put right here to write a plane? Any guesses?
Say a P.
Nope. You have to write the word plane. To write the word plane. So you have to write plane, CDE. That's how you write planes. It has to be a minimum of 3 points, right? 3 points. And you have to write the word plane. That's notation. Physical word plane. Alright. It's been a while. It's been since August 25th since we probably wrote that. So it's been a while. Alright. Now, the next one, right? We talked about lines. Lines contain at least 2 points. A plane contains 3 points, at least, a minimum 3 points. So again, just like I said earlier, if you're given a flat surface, you can put at least 3 points on it. So, M, N, and O. You can put 3 dots not in a straight line, but put 3 points on it. Any 3 points you want. And then you can name it, just like I said earlier. Plane M, N, O. In no particular order. Right? I just wrote the 3 letters up there. right, so now, the first four are really easy. They make sense, right? You talked about lines, they have points. If you have points, you can make a line, that type of thing, or planes, same, vice versa. The next three, 3, 9, 3, 10, 3, 11, now we start talking about the interaction of these objects. We've been talking about lines and planes, but what happens when you start mixing them together? So, 3, 9 here talks about two lines two points, and they're on a plane, right? 2 points that lie on a plane. So let me draw this out here for you. So you have your plane, and I have 2 points on it. Let's call this X and Y. 2 points that are on my plane. Again, this is 3.9. Then what they're saying is that the line that contains those points also is on the plane. Well, that makes sense, because if I go back to 3.5 here, right? 3.5. 3.5 talks about, through any 2 points, there's exactly one line. So again, I have 2 points drawn on this little piece of paper, this little plane. So I can draw one line through it, right? Boom. iPad moved on me. Boom, there you go. So I have 2 points, lines drawn through it. Well, what they're saying is that the line is also on the plane. Well, it makes sense. I mean, if you look at my marker board right now, the line is drawn on the marker board. It's on the single flat surface those two dots were found. It doesn't suddenly poke through the paper and go through it. That would be a curve. All right. And then 310 and 311 talk about interactions of the object. So instead of a line or a points and planes, now I'm talking about two lines crossing. So if two lines intersect, that's called an intersection, right? It's a point of crossing with two lines. So let me draw this out. We have two lines that cross. Here's my two lines. They will make one single point in the middle, point P. And this is the part that I want you to kind of wrap your head around. We've talked about, a point is an infinitely small point, right? It's a location in space labeled with a capital letter. That's the definition of a point. To draw a point, you need two lines across. And if you have a line, lines have 2 points on them, according to 3.7, right? If you look up above, a line contains 2 points, right? So it just spirals out of control. Every time we have a point, we have to have two lines crossing. So you can start to see the complexity of, like, when you start drawing these objects, there's a whole network of lines that are connected just to draw objects, because every point needs two lines crossing, and every line will have 2 points on it, and vice versa, just spirals out of control. So it's kind of hard to wrap your head around once you see the connection there. Then on the last one, two planes that intersect. So I have two flat surfaces. I don't know if you'll be able to see this. So here's one flat surface, and I have another one crossing it over here. Well, when they meet, they form, a line. Two planes intersect to form a line. And you can see that here. The line goes right down through the middle. So, Miss Scott, if you can point out, like, where the two walls meet in the corner, there's a line. I don't know if they can see that. Yeah, especially in the room, you can look at, like, where the ceiling meets the marker board wall. You can see there's a definitive line on the wall. Where the two marker boards meet right in the middle, right in front of you. I mean, there's a metal bar right between the two marker boards. Those are two flat surfaces connecting, right? They make a line. So now you're starting to see really complex ideas that, to make a point, you need two lines crossing. To even make one line, you have to have 2 points on it, which also means you have planes that cross, and that makes more points, and it just spirals out of control. But these postulates were found scattered throughout your textbook, and I kind of combined them all into one. So these are technically not the correct postulate numbers according to your textbook, because they're kind of all over the place. But I thought this is kind of a good idea to pull them in so that you could see how they're all kind of working, because this whole unit was about lines and planes. So I mean, it makes sense that we should talk about them now.
Anybody need more time with that one? Nope, they're good with that one.
Okay, last property today, I promise you. This is the last, absolute last property. Here you go. Last one of the day. It is Theorem 310. It's a theorem now. Midpoint theorem. M is the midpoint of A to B. Then A to M is equal to M to B. And it's congruent to, maybe I should put a little congruency symbol. There you go. A little tilde above that thing. That's an equal sign with a little tilde above it. That means congruent. It's a congruent symbol. You have to talk about congruent when you talk about geometric objects. Proof of this one's really short. Just uses distances. So it's called the midpoint theorem. Alright, so we have some type of segment A to B, and again this is a segment, there's no arrows above A to B on that thing, so A to B, and they're telling me M is the midpoint. So again, definition of midpoint, it's the center of an object. It's the perfect center, it's the midpoint, it's the midway point between things. They just literally put like middle and point and crammed it together and said midpoint. Definition of midpoint, according to your textbook, means the distances are the same, like the actual the physical distance here. So, you know, if I had the measure of this, right? Let's call this distance number 1, and I measured this one, and this is distance number 2, right? And I actually physically measured them. The definition of a midpoint means those two distances are equal. D1 is equal to D2 in terms of digit numbers. Right? 3 inches, 3 inches, 4 inches, 4 inches, that type of thing. So it's the middle, but it also means the distances are the same. We use that, I think in the first unit test, we use distances. Now, if the distances are equal, that means the measure of A to M, whatever that is. So how you write that, you write A to M, and notice I leave the little bar off the top. That's how you measure it. That's equal to the measure of M to B. By leaving the bars off the top, that means the measurement. So I measured AM, that equals the measurement of M to B. So again, I left the little bar, and those are equal because I'm talking about the actual physical number. Numbers are equal to each other, right? Objects are congruent. And since the measures are equal, then I can write that these objects are congruent to each other. The physical objects. Again, we talk about the actual physical lines are congruent. The word congruent here, we've had this on every chapter test that's had vocab on it. Congruent is equal in size, shape, and measure. Well, they're the same shape, they're both segments, right? They're the same size and proportionality, and they're exactly the same measurement. So they're congruent to each other. So that's the whole proof you're looking at right there. It's really straightforward. It talks about the definition of midpoint, talks about measurement, and then it talks about those measurements make it congruent. So that's it for today. That's all I have. So it's a lot of properties, I know.
Did everyone get a chance to get this one down? Alright, I'll have that one.
All right. Thank you, Ms. Scott. Thank you, everyone. Remember, check your grade book. See if you're missing anything in JMC. If you are, make sure you go in Google Classroom. Everything's in there. Go turn in your homework. I know a lot of you haven't been turning in stuff. Go get it submitted to me so that way I can get it graded. Semester test for us. Because I know every teacher is going to be posting semester tests this week, right? When it's going to be, because some semester tests are coming up at like the end of the week. So keep that in mind. My semester test will be the Tuesday when we're back after winter break. So the reason why I'm I usually like to have mine before winter break. I'm putting it after. The reason why I haven't been there in a week. It's not fair. So I'm going to put it after, and we'll start reviewing this Thursday. I always like to do a 5-day review leading up to it. The semester test for you guys will be 10%, not 20% of your grade. 10%, just because I haven't been there, and it's kind of a weird year, and some of you are not there a lot, and so because of sicknesses and whatnot. So I'm going to make it 10%. So that's more than fair because we have to have one. We're required to. So I'm choosing the bare minimum, what it's worth for your grade. So, all right. But yeah, we'll start reviewing it. You'll get a physical copy in your hand, on Thursday this week. So, all right. Well, thank you, Miss Scott. That's all I got.
All right, perfect.
All right. Thanks.